sentence. So I've set up my tree diagram, and it says 10% of the time the athlete actually takes steroids. So the complement would be that tells us 90% don't. And then it says the test is accurate 95% of the time when they take it. So 95% of the time for the people that take steroids. So that would be 5% of the time it would say negative. And then here it is 97% accurate when they haven't taken it. So accurate, it would be accurate, meaning 97% of the time it should say negative, because again, the test would be correct. If they don't take it, it should be negative. Okay, so that might be the trickiest part. Now the math is pretty straightforward. We're just gonna multiply through here. So we take 0.1 times 0.95. And 0.9 times 0.97. So the majority of the time, people don't take steroids. And again, you can think that this as 1,000 out of 1,000 people. So out of 1,000 people we might test, 873 of them don't take steroids, and they would test negative for steroids. So now if we kind of understand what each of these four numbers mean, and they also should add up to 1, then it is probably helpful to answer the second part. So this is A, make a tree diagram, and B, what is the probability that a randomly selected athlete tests positive? And so notice these are the two groups of people testing positive. So it would be these 95 people plus these 27 people out of a total of 1,000 people if I tested 1,000 athletes. Well, that would be like adding 0.095 and adding 0.027. It's important to me, though, that you understand why they're adding and why that would make sense. So in the back of the book, the answer is, if I added those together, I get 0.122. Okay, so 12, a little bit more than 12% of the time, people test positive. So that's the probability of testing positive. Now remember, some of the time I'm testing positive because I took steroids. Other times I'm testing positive because it's just a false positive. 3% of the time the test is wrong when I don't take it. Now the next question they're asking me is, what is the probability of testing positive? What's the probability that he or she actually used the steroids? So suppose they did test positive. So what they're saying is, what is the probability it is actually used steroids given they test positive? Okay. And so this is when I have to tilt my head and see a fraction here. So I want to ignore the other data I've collected and only focus on the people that tested positive. So what they're asking me to do is tally up the number of people that tested positive. So here they are, and we've already kind of tallied those people together. So I have 95 people, and I have 27 people. So out of just those people, and again, those were the people out of 1,000. So let me add that up. So that's the 122 people. So for every 1,000 people I test, 122 people I would expect to test positive. And out of those, how many actually took steroids? So these 95 people would have been the people that took steroids, because these 27 people tested positive, but they didn't take steroids. And that's what they're asking us. This is actually considered the relative proportion. Okay, so comparing only the people that tested positive what proportion took steroids. So when I take another look at this, I notice that this is what was listed in the back of the book. Using formulas, but I think logically it might make more sense to work our way through that. And these two fractions should be exactly the same. So 77.87 would be that number. And so that logically makes sense as well. 77% of the time, if you tested positive, you were taking steroids. All right, last question. It says build a two-way table, and we're pretty good at that. So I actually feel pretty confident about this one. But it's, again, very good practice because I think two-way table is the most useful tool to start with. So it says, working at Mike's Pizza, you have the following information about 7 pizzas in the oven. 3 of the 7 have thick crust, and 2 of the 3 thick crust have mushrooms. Of the 4 remaining pizzas, 2 have mushrooms. Choose a pizza at random from the oven. So, working our way through the problem, it looks like either a pizza has mushrooms or they don't have mushrooms. So we can work our way through this little by little. It says, in the oven are 7 pizzas. 3 of the 7 have thick crust. And 2 of the 3 thick crusted pizzas have mushrooms. So we know 2 have mushrooms. Okay. Then it says of the remaining 4 pizzas, 2 have mushrooms. 2 have mushrooms. So it seems pretty obvious. I'm anticipating 4 with mushroom and 3 without mushroom for a total of 7 pizzas in the oven. If I just read the question and I only think about mushrooms. Now going back through the problem, I have to focus on this idea of thick crust. Okay, so thick crust and not thick crust. So it says, in the oven, 7 pizzas, 3 of the 7 have thick crust. Okay, so 3 of the 7 have thick crust. Now we're looking for our overlap. So reading it again, 3 of the 7 have thick crust, and 2 of those with thick crust have mushrooms. So we know 2. Okay, once we have this, we can fill in the table with the complement rule. So this would be 2, because 2 plus 2 is 4. This would be 1, because 2 plus 1 is 3. This would be 2, because 1 plus 2 is 3, and 2 plus 2 is 4. And we have a perfect table. Now, remember that this is our raw data. And this is the data we have to think about as actual pizzas, imagining them there in the oven. So this is our data. Now that we know the data we've collected, we can answer questions on it. So A says make a two-way table, and we did that. B says, are the events getting a thick crust and getting a pizza with mushrooms independent? So, very interesting. We knew we were going to get a question like this. So let's try to go through step by step and answer it. So what they're really asking here is, we know it wouldn't be independent if the probability of mushroom did not equal the probability of mushroom given thick crust. So if these are equal, the probability of mushroom given thick crust, if they're equal, then it's independent. And it doesn't look like it's those would be equal, but let's test that out. You also would have to test out, or you could also test out what's the probability of thick crust, and if that would be equal to the probability of thick crust, given you have mushrooms, that would be another way to say, yep, if those are equal, then it's independent. Knowing if they have mushroom doesn't help me figure out if it's thick crust or not. Okay. So walking through the math here, what's the probability that you have mushroom? So I'm just ignoring everything, and mushroom, the probability of mushroom would be 4 out of 7. And Now, probability of mushroom given thick crust. So given thick crust means I'm going to only think about my thick crust. It looks like 3 would be my denominator. So the probability of mushroom given thick crust, I need T, or the total of my thick crust, to be my denominator. And out of those 3, 2 have mushrooms. And so I can kind of see here that 4/7 doesn't equal 2/3. One good test is when I cross multiply, the number 14 does not equal 12. So I can say they are not independent. Okay. And again, I could also do it the other way around. The probability, what's the probability they have thick crust? It looks like 3 out of 7 of them have thick crust. And what's the probability of thick given mushroom? So ignoring everything, there are 4 mushrooms. So I can put the 4 mushroom on the bottom of my denominator. And out of those 4 mushroom, 2 are thick. Now we notice the ratio 3/7 doesn't equal 2/4. Or once again, notice we get the same numbers here. 14 does not equal 12. So I come to the conclusion they're not independent. Last piece of it. It says you add an 8th pizza to the oven. This pizza has thick crust with only cheese. Now are the events of getting a thick crust pizza and getting a pizza with mushrooms independent? Explain. Well, this one is going to be the bonus. So if you're interested in looking at this one on the test, check out the answer in the back of the book and let me know if you have questions in class.